Hi, and welcome to the UAS Ketchikan Campus Library. I'm Lana Clark. Thank you, everybody, for being here and braving our hill. I just wanted to let everybody know that as members of the public, you do not have to be a student to get a library card here. You just need to be a Ketchikan resident. And then also keeping in mind that we are live streaming this, so if you guys have any questions, your voice will be on the recording, but if you're not comfortable with that, you can write it down and I'll ask the question for you. I'd like to introduce Dr. Jackie Vogel, Professor of Mathematics with the Alaskan Peay University in Clarksville, Tennessee. Dr. Vogel received her Bachelor of Science in Mathematics at Carson Newman, Masters of Education, Masters of Mathematics, and Doctorate in Education at the University of Tennessee. Thank you for joining us.
Thank you for having me. Welcome. So I don't frequently talk with slides, but this kind of talk needed slides, so I'm going to have to kind of look at it, but it's not my normal mode. So if I seem kind of clunky, I am, sorry. And the live streaming, if I move around, are we okay? Do I have limited space?
You're starting to get off the screen right about there.
I was just trying to figure out where I could be so I could see this and see
That's
them.
right in the middle.
All righty, cool, that works. Okay, so what do the Alaskan Kaktovik Numerals and ancient Mayan numerals have in common is what we're going to talk about. But we're going to talk about a little bit about counting and leading up to it and how we got there to start off before we get to the connection. So you're going to have to hang on, it's coming. All right, so how counting started. Counting without numbers. So they started like pointing at things and matching things with pebbles, things like that. So not with numbers. So in the recent past, the Vedas of Sri Lanka used one pebble for each item using words like single, a couple, another one, and many. So they didn't have words for even the numbers, just here's a pebble for a single one. Then the Peay of Papua New Guinea used body counting by pointing to body parts like the left little finger for 1, left neck for 11, right ear for 16. Their largest number was 28, shown by clenching two fists together. So that's the biggest number they had, was 28. And it was common to use the body for counting. Body counting was used as recent as the late 1800s, including the native peoples of Paraguay, whose largest number was 20, pointing to 2 feet. So this is logical for us because we got 5 fingers on each hand, so that's 10, 5 toes on each foot, so that's 20. So 20 became a common number in this body counting process. Okay, another thing they did was notched bones. So about 15,000 years ago, you can find bones that have notches on them. So it's like tally marks on a bone. So another way to count. Then came abstract counting, which is used by the majority of people today. So this idea of clenching fists and pointing at our feet and our neck and things is cumbersome. So how could we count matching objects, abstract counting? So you can count anything that way, and you can go on to infinity. So we came up with this system. Let's say I can think of the biggest number I can think of. What's the biggest number you can think of? Infinity. So I could add one more to it. Infinity plus 1. We can keep going. All right. The Sumerians developed a numeral system about 5,000 years ago. So now let's start putting some numerals with these words. So starting about 1500 to 500 BC, the Phoenicians, Greeks, and Romans had limited sets of numerals. Have you worked with Roman numerals? It's clunky, it's weird. There's no 0. It's not as clean as the system we're using now, but it worked. And they're still being used for certain things now. What do we use Roman numerals for still? names? Super Bowl, that's the one everybody knows. That's the only Roman numeral some people ever use is the Super Bowl. So we still use the Roman numerals. So the Arabs brought the Arabic numerals to Europe around 1000 AD. They called these digits Hindu numerals because they borrowed them from India. Around 1650, the Arabic numerals were accepted in Europe and are what we use today. So sometimes we call them the Hindu Arabic numerals, but when we draw a 1, we draw a 2, we draw a 3, those funny little squiggly marks we made, did you know that came from Hindu Arabic numerals? So it's not ours, we didn't invent it, but 1650, that's only like 400 years ago. So we've only been using this funny little set of squiggly marks for 400 years. That's not very long. Okay, so with our funny little squiggly marks, we have all different kinds of bases. Notice that I've highlighted decimal base 10. Why would I highlight decimal base 10?
Because that's what we use.
Because that's what we use. So now thinking back to the body counting, why do we use base 10? Exactly. 10 fingers. And base 10 is really easy to use because what happens with powers of 10? Add 0. 10 squared is?
100.
10 cubed is? So it's really easy to work with it because it's just multiplying by 10, so it's just adding 0. So decimal makes sense. But all these others, did you know the names of any of these others? Binary. Why do we know binary? Coding. Okay, what else? That's the only one that's familiar to you? Yes.
Octal, just because like octagon stuff.
So octal, octagons, 8-sided. OCT means 8, so that's base 8, and that is used also in, there's a common place octals used. Computer. Okay, did you say, what did you say?
Hexadecimal.
Hexadecimal. That's another one that's commonly used with
Space.
space,
Physics.
physics,
Science.
science,
Computing.
computing. Okay, so why binary, base 2, octal, base 8, hexadecimal, base 16? Why are those common in computing? Well, what's 2 to the 3rd power? 8. What's 2 to the 4th power?
6.
So their powers of 2, and binary is 2, 0, 1, on, off. So it's natural that octal and hexadecimal get used for computers. Okay, so I must admit that ternary for base 3, did not know that word. Quaternary for base 4, I've heard it but didn't remember it. Quinary base 5, I did remember that one. Centenary base 6, nope, didn't remember that name. Septenary base 7, vaguely remember that for the same reason you remembered octal, because septagon is 7-sided, so it fits in with that. So sept means 7. Octal, nonary base 9, no, I don't use that name much. Undecimal base 11, didn't even know it had a name. Dewey Decimal, that I did know, base 12. So have you heard Dewey Decimal before? Library! The library uses the Dewey Decimal System. Okay, now, hexadecimal, base 16, we got that one. Bigesimal, base 20. That one's going to come into play in just a little bit, so remember that one. The sexagesimal, base 60. This one is very useful too because it's powers of 60. So, what is 60 squared? 60 times 60. 3,600. Okay. 60 times 6 is what? 360. So if you think about 60 and you think about 360, what do you think about out there in the real world? Turtles?
Circles.
Circles! Ah, that makes more sense than turtles. Circles. 360 degrees in a circle. How many seconds in a minute?
60.
How many minutes in an hour?
60.
So how many seconds in an hour? 3,600, which is the 60 squared. So the base 60 is very useful with degrees and minutes and seconds and hours and those kinds of things. Plus, 60 is divisible by 2, 3, 4, 5, so many different numbers, it's easy to work with it. Okay, so now just for fun, here's some places where they are used. Do you recognize any of those? When we talked about base 4, did you say something about biology?
No, but it makes sense.
Yeah, it made sense. DNA, binary grouping, 2 squared is 4. Base 5, body counting, we've already talked about that. 5 fingers, 5 toes on each hand and foot. Base 6, NCAA referee signaling. Did not know that. A lot of it happens with cryptanalysis and cryptography, and that makes sense to me. The base 8, computing and avionics. Base 9, number theory, casting out nines, unit digit analysis. So there's a lot of interesting stuff, the higher level math that happens with base 9. Base 10, money makes sense because the decimal, 10 cents, 10 dimes in a dollar, $10 bills and a $10 bill, 10 tens and 100s. So it works well for money. Medicine, metric, percents, probability works well with base 10. Base 11, music theory, ISBN check digits. So they can check to see if the ISBN number is correct using base 11. Measurements for Dewey Decimal, inches, times, music scales. Do you know music scales based on 12?
Yeah.
Now, base 20, big decimal. Money and currency. You got 20, you got 5 $20 bills and 100. Times and years. 4 score and 7 years ago. 4 scores, a score is 20. So 4 score and 7 is what? So 4 score means I've got 4 20s, 87. So did you realize that? Okay. So now the base 20 comes into play with indigenous languages, the Yupik and some African languages. So that's where we're going to circle back to the base 20 in a little bit. Sexagesimal, base 60, time, angles, coordinates, latitude, longitude, and astronomy. So a lot of that, the 60 comes in really well with the degrees and such. Okay, so how it started. The Alaskan Inuit language, Inupiaq, uses an oral counting system based on the human body. So circling back to the human body. So oral counting system, for example, talamat means 5 and comes from talik, the word for arm. One arm typically has 5 talamat fingers. I am not going to necessarily pronounce these words correctly, and forgive me for the mispronunciation. And Lana, if you can jump in and correct me if you know if I'm saying one wrong, I have no problem with that, because this isn't language that I'm used to. So I'm assuming I'm pronouncing that correctly, but it's okay if I'm not. Just correct me. And here's where I need help. Inuak represents 20 and the whole person. So remember a minute ago we had one of those where 20 was the whole person with 2 fists? So same thing's happening here. There were words for the numbers, but no symbols, so the default was to use the Arabic numerals. So they had the words, but they had no symbols because it was an oral language. So we had the word talamat, which means 5 fingers, 5, but we didn't have a symbol for 5. So remember that the Hindu-Arabic numerals, the little squigglies have been hanging around for about 400 years. Let's just use them. They're already out there. They're commonplace. And so that's what they did until about 30 years ago, a middle school teacher in Kaktovik inspired his students to create numerals to accompany the Inupiaq number words in 1994. So he's telling the students about this, and they're like, well, why don't we have our own symbols? Why do we have to use the Hindu Arabic symbols that we've been given? So he's got 9 middle school students. It's all the middle schools all the students in that middle school. He said, let's come up with our own symbols, our own numerals. And why and how it caught my attention. So I like to do study abroad. And I used to take students to Jamaica. And we would have lots of fun looking at things mathematically in Jamaica. But then they went to a level 3, and then to a level 4, and back to a level 3. But that meant I couldn't take students because it has to be a level 1 or level 2. So students can't travel to Jamaica anymore. It's back to a level 2, but the area that I go to is still a 3. So I still can't take students to where I want to go in Jamaica. And our university said we would like to do more study away, not just study abroad. And so it would be easier because we won't need a passport and we can go to places in the UAS. And about the same time they said that, I read about the Kaktovik Numerals because in 2023, I think it was, they made the Unicode for it, if I'm saying this right, so that you could type it on the computer. And so an article came out in Scientific America, and I read the article and I'm like, oh my gosh, this is so cool. So I said, can I take students to Alaska and we can explore the Kaktovik Numerals? And the answer was yes, and so here we are. So I'm here with students. I've got math students. Dr. Haas has science students, and they've been studying these numerals and their connection to the Mayan numerals. So here's what we got. The Inupiaq numbers, there's the words, the language we had, and here are the numerals the students came up with. I have them on some tiles that have been 3D printed, and I wanted to bring them with me, and I realized I didn't have them, and because of the weather, I wasn't going back to get them. So I could have had visual aids for you, but I wasn't going back because the roads are rough. So the cool thing about the system that these students came up with is it's very intuitive, and it works well together. So if you see downward slash for 1, but if you want a 2, all you got to do is take 2 1s and mush them together. And now you've got a 2. You want a 3, take a 1 and a 2, mush it together. Can't do it. There we go. Mush it together, and you've got a 3. Or you could just take 3 of the singles and mush them together. All right, so we want a 4. 2 plus 2 is 4. There it is. So now we've got 1, 2, 3, 4. We get to 5. 1, 2, 3, 4. What do we do at 5? So this is a base 20 sub-base 5 system. So that means that we've got 20 numerals, 20 digits, and we've got to 5, so they made a slash this away. So we're going down this away for 1, we're going over this away for 5, so that made it real easy to get 6 because we can have the 1 going this way, we'll put the 5 and the 1 together, and you've got the 6. And then it keeps going from there, so it was very intuitive. Okay, we're trucking along, and we get to 10. Well, if this slash is a 5, how are we going to make a 10? Put 2 of those together, exactly. Now we've got the 10. So then if we want 11, we've got the 10. We just add a 1, and I don't have enough hands now to do it, and you've got your 11. So they keep going, and they get up to 19. Because we get to 15, now we've got 1, 2, 3 slashes going horizontally for 5, 10, 15. Then we've got 1, 2, 3, 4 this way and attaching it, so we've got our 19. And they said, we don't have a 0. What about 0? Poor 0, it's been an afterthought in a lot of numbers. If we go back to the Roman numerals, where's the 0 in the Roman numerals? There isn't one. And so, do we use the Roman numerals as our standard system of numbers today? Nope, because it doesn't work well without a zero. So they figured out they don't have a zero. They said, what are we going to do about zero? And one of the students went, I've got nothing, and now you've got a zero. So we have 0 to 19. 0 to 19. How many different digits is that? 20. And so it's a base 20. And when do they chunk? 0, 1, 2, 3, 4. Now we start with the slash, so we've chunked them in 5s. 5, 6, 7, 8, 9, 10. Now we've got the 2 slashes, and so it's base 20, sub base 5. And I'm like, this is fascinating. This is so cool. We got each hand, we got each foot. It's intuitive. It's interesting too because the students' math scores after they spent time creating the system went up. They owned it. All right, so then I got to thinking about the Mayan numerals. Guess what the Mayan numerals are? Base 20, sub base 5. They map exactly the same. So if you look, shell for 0, there's other symbols for 0 too, like faces and stuff, but shell's common with our I got nothing for 0. Okay, we have 1 slash for the Kaktovik for 1. We have 1 dot for the Mayan. We have 2 slashes for the Kaktovik. We have 2 dots for the Mayan. You see how they're following each other? So now we've got 3 slashes for 3, 3 dots. 4 slashes for 4, 4 dots. What happens when we get to 5? It changed to a bar. So it's following that same sub-base 5 system. So now we got a bar for 5. How do we get 6? So we got our bar and we add a dot for our 1. So same thing. On our Kaktovik for 6, we had our 5 and our 1. For mine, we have our 5 and our 1. Is that not cool? This is cool. This is really cool. So this actually got me thinking, like, for the Kaktovik and the Inupiaq, the words, is there a connection with what's going on in the native Alaskan with what's going on down in Mexico? Is there somehow, are they connected because they're following the exact same pathway? You should be excited. This is exciting stuff. Okay, so to help you from the math perspective, I did add a slide for the decimal base 10 versus the decimal base 20, so you can see that the ones place, 10 to the 0 power is 1. 20 to the 0 power is 1. So your ones place is the same. Now, when you go to your tens place, 10 to the 1 is 20 to the 1 is 20. So the decimal is bundling them and chunking them in tens, but the Kaktovik and the Mayan is bundling and chunking them in 20s. So if I needed the number 40 in base 10, what would I have? 4 tens. I would have 4 tens. If I needed the number 40 in base 20, what would I have? 2 20s. 2 20s. So then we go to the hundreds place, 10 squared is 100, but what's 20 squared? 400. 400. So these are going to bundle and chunk quite differently as soon as we get away from the ones place. Also, something interesting here is the Mayans veered off a little bit in that hundreds place. For their calendars, they use 20 times 18 instead of 20 squared in that place value for the calendar. What's 20 times 18?
360.
360. Why would they do that?
Circle.
Yeah, and the year is approximately 360 days. If you have 12 months, 12 will divide into 360. They had lots of reasons to do that. And so that makes it not as smooth when you're looking at the Mayan calendar numbers. But then they go back to 20 cubed for that thousands place. Okay, so now we've got some examples. For 21, I have 2 slashes for the Kaktovik, and I have 2 dots for the Mayan. So what's the first thing you notice about the Kaktovik versus the Mayan?
One is sideways, one is reverse.
Exactly. So the Kaktovik writes it like we do, but the Mayan stacks it. So that first slash says I have 120, and the second slash says I have 1-1. For the Mayan, the top dot says I have 120, the bottom dot says I have 1-1. So when we get to 40, what's going on there with the V and the squiggly thing? What's happening? What's the V worth?
2.
What place value is it sitting in?
20.
The 20s place. So what does that tell me?
We have 2 20s.
We have 2 20s. What's in the ones place?
A 0.
A 0. So 2 20s and a 0. So with the Mayan, what's going on there?
2 20s and a 0.
2 20s in the 20s place and a 0 in the ones place. So it's stacked up. Okay, 123. Now it's going to get really messy. How does that represent 123 in the Kaktovik? What do we got here? What's that?
6.
So 5 and 1, so that's 6. Then I've got this. What's that?
3.
So I've got 6 and 3. How do I get 123 from that?
6 times 20 is 100.
6 20s is 120 and 3 ones. Okay, so with the Mayan, with the Kaktovik I had this, with the Mayan, my 6 is my bar and my dot, so what's happening there?
Showing that we have 6 20s.
We have 6 20s, and my next place value, I have
3 1s.
3 ones. Okay, here's your challenge. Can you tell me what 62 would look like in the Kaktovik? Okay, so I've got 3, because I've got 3 20s. And then 2, yes, that's it. Okay, all right. So now because the Kaktovik and the Mayan are essentially the same, it's just using different symbols, and this is going this way and this is stacked this way, what would 62 look like in the Mayan? 3 dots on top for the 60, 2 dots on the bottom. Yeah. All right. 57's challenging. Can you do 57? And we'll make the math people wait to see if the science people can figure out 57.
Do halves.
Hmm?
Can you do halves?
Can you do halves?
2 1/2. So
Start with how many 20s are in 50. Okay, so can we put a half in a place value? Okay, so that means the most 20s we can get is 2. Okay, all right.
it would be the one for 2 20s and then 17.
2 20s and a 17 is exactly what it would be. Nice job. Oh, look, you're getting accolades from the math corner over here. Okay, there you go. There's the answer. There's your answer, Keith. Does it look the way you expected it to? Yay. All right, so it turns out that this works really well with operations You see the addition, the 2 plus 2 gives you the 4. 4 minus 1, if I started with the 4 and I took 1 off, it gives me the 3. So it's really smooth how it works. The 6 times 3, multiplication's a little messier. It looks like we're doing a little bit of distributive property. Division, I think, is also messier. They're using colored pencils, but it actually works out pretty well too. You just have to think a little bit more about it. Now, the thing in the center, I also had that with me, and it got left at the hotel too, is a base 20 sub base 5 abacus. And the reason I had one with me is because I showed it to my husband and I said, can you 3D print me this and make it for me? And he did. He had to order the little metal pieces for the bars, but he put the rest of it together. So the reason this is a base 20 sub base 5 abacus is if you look at the ones place, you can see the 1 white bead moved up. So that'd be 1, then 2, 3, 4, slide it down, slide down, you got 5. Then up 1 bead, 6, 7, 8, 9, slide it down, so you got 2, so that's 10, then 11, 12, 13, 14, slide it down, you got 15, 16, 17, 18, 19. Now slide them away and move up 1 and move over to your 20th place. Do you see it? It's really cool. Can you see it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and now you move to the next place, right? It's very cool. The first time I saw it, I had to think real hard. What is this? How does this work? I had to actually count it through to figure it out. All right. Oh, that's it. Okay. Well, questions? Yeah. Did I go way fast? Yeah. Oh, okay. All right. Questions? Suggestions? What should I do differently? What did you like? Yes.
So this was 94, so that's been about 30 years.
Mhm.
Do they still use the system?
Oh, that's a messy question. So,
Oh, I know.
no, I'll